Okay. Hello everyone. Welcome to today's Dream Seminar. Today we're very fortunate to have Sharan Song here as our speaker. Sharan is a professor at Columbia University in the Department of Computer Science and does research on robotics and computer vision. I've been particularly excited about her work on robot manipulation of deformable objects and leveraging dynamic actions in robot manipulation, such as the FlingBot work that she's going to talk about, which I just heard is a finalist at Coral. Sharan completed her PhD in computer science at Princeton University in 2018. And before that, she received her undergraduate degree in computer science from HKUST. During her PhD, Sharan spent time working at Microsoft Research and also Google. She's received a number of awards, including the Best Systems Paper Award at RSS 2019, the IEEE Transactions on Robotics Best Paper Award in 2020 for her work on robot tossing, an Amazon Research Award in 2020, and a TRI Young Faculty Award in 2021. She's also a 2021 Microsoft Research Faculty Fellow and was part of the MIT Princeton team for the Amazon Robotics Challenge, winning the third place in 2016 and first place in 2017. Today, Sharan's going to be speaking about her work on interactive clock perception. I'm especially excited to hear this talk since perception is so critical to learning reliable ways of handling deformable objects, which is very important for improving robots' ability to act in the world. We'll have time for questions at the end of the talk, but also if you have questions during the talk, it's fine to unmute yourself and ask your question. So Sharan, thank you so much for being here, and we're all really looking forward to your talk.
Thank you so much. And yeah, so my talk is about interactive clock perception. And I really intend to make this talk also more interactive. So if you have any questions, any doubts throughout the talk, just directly unmute yourself and ask the question. I unfortunately cannot see you guys' faces or see the chat. So I will not be able to see the questions in the chat window, but just feel free to unmute yourself and ask questions.
By the way, really quickly, I'm seeing a grayed out box in the middle of the screen. I think Daniel just put in the chat that he sees that as well. Okay, it just went away, great.
Yeah. Okay, great. Yeah, that's a notification about the recording, but nice, good. Okay, so we can get started. Okay, so let's first talk about deformable objects. That's the main topic of today's talk. I think deformable objects really, as we all know, it's really everywhere in our everyday life. And if I just ask you to take a quick look around yourself, I bet you'll probably find way much more deformable objects than the ones that are completely rigid. And therefore, no matter what kind of applications that you really care about, either home robots or industrial applications, deformable object is something that we all agree that is something that we cannot bypass, or we eventually all need to handle. So of course, there is a wide spectrum of deformable objects that's out there. So from things that's just barely slightly bend under external forces or pressures, examples like spatulas or stuffed animals, to things that's much softer like papers or cloth. So all of these objects could be considered as deformable objects. However, the difficulty of handling them are very different. Right? So in the context of today's talk, I will mostly focus on the category of deformable cloth, which I think presents a set of very unique properties, making them extremely difficult for robots to perceive or interact with. And here I'm going to show you a short list of examples of those properties. So first, I think deformable objects often presents extremely high degree of freedoms, right? So in particular, in contrast to rigid or articulate objects, whose pose or configuration can be easily specified with just a few numbers, a piece of garment or cloth can easily have near infinite degree of freedom. So how to efficiently represent and infer their full configuration is one of the biggest challenges for handling them. And the second challenge is also the class or deformable class is highly under-actuated. So what that means is that when a robot is holding a piece of garment or piece of cloth, all it can control is a very small region on the cloth around its gripper. And the rest of the cloth will just be hanging there, and the system do not really have any direct control over those out of contact positions. which is very different from objects like spatial or stuffed animals, which the robot do have controls of those out of contact positions. And the third is more about their 3D geometries. So for objects like cloths or garments, they often consist of very thin 3D geometries that are not watertight. So this kind of unique geometric property makes them often ill-suited for typical 3D shape representations that are typically designed for solid or rigid objects, such as occupancy grid or sign distance function. Therefore, it really requires us to think about new shape representations to represent this kind of thin 3D geometries. And finally, because deformable cloths is so thin and they can deform in so many different ways, they often experience the most extreme case of self-occlusion. Right. So for example, here I just showing a few example images where the ratio between the observed surface with respect to the full surface of this garment can be as little as 10% in many real-world applications, which makes the perception and the planning task extremely difficult. So because of all these challenges, prior works on garment or cloth manipulation oftentimes build on top of several simplifying assumptions. So for example, they can assume high visibility of the cloth, where the cloth is only considered as it's already worn by a person, which pretty much all the surfaces is already visible, or rely on very strong prior knowledge about the cloth or the garment, such as very accurate instance level mesh, or full state information in initial observation. As a result, the state estimation problem become just simplified to a tracking problem. So in today's talk, the high-level goal is really trying to realize some of those assumptions a little bit and really try to answer the question of how we can effectively perceive and interact a piece of cloth under this kind of severe self-occlusion. So basically, I will talk about two projects. One is mostly focused on perception, and the other focuses more on manipulation. But more importantly, I also want to discuss how we could kind of integrate a robot's perception and manipulation capabilities in order to make them mutually benefit each other. Right? So for example, how to use robot's action to simplify the perception task, and also leverage the perception results for more precise and robust manipulation. So I call this general direction interactive cloth perception, which is something I'm personally very excited about. And for the last part of the talk, I'm intending to make it more like a discussion instead of a presentation, so that I can also hear about your guys' idea and suggestions, since I know that many of you guys are actually actively working on this area. So I'm really excited about that. Okay, so we can get started on the first project, which is on cloth perception, where the goal for this project is to do category level post estimation for garments. So this work is done by my student Cheng, and this paper is just recently presented in ICCD last month. So the goal for this project is to do post estimation for garments. But the first question that we should ask before we even start this project is how we could define the pose of a piece of garment. Right, so for rigid objects, the definition is very clear. So given any object instances, its pose can be fully described by 6 numbers, 6 degrees of freedom, which consists of 3 degrees of freedom of translation and another 3 degrees of freedom of rotation. And then in order to extend this definition for a collection of object instances, which we call category level pose estimation, we can try to define a shared category level canonical pose. So for example, for a given category like cameras, we can use the direction of the lens in order to align all the different object instances, and then use that orientation to define a shared canonical pose for this category. So, and then the task of category level pose estimation is then defined by inferring the corresponding transformation between the observed object instance to this canonical pose, where the observed object instances can be something that the algorithm never see before. And we call this representation NOX, which stands for normalized object coordinate space. And a similar idea also can be extended for articulate objects, just with a few additional degree of freedoms describing the object's joint parameters. But the question is how we should define pose for deformable objects like t-shirt. Are we going to kind of specify the position of every single vertex on this object? Well, the short answer is actually yes. And because since a garment has such a high degree of freedom, in order to fully specify its configuration or pose, we kind of need to specify every point location on the t-shirt surface. And what's more is that we also need to specify the position of for both observed and unobserved surfaces. Since we no longer can use the rigid body constraints, we cannot directly solve the pose for unobserved points using algorithms like RANSAC. So obviously it is a lot for the network to inference. However, since all the degree of freedom are not completely independent, they have very strong constraints or prior that the algorithm could leverage to simplify the problem. So the question next is how we could impose those constraints or prior knowledge. So again, we can define a category level canonical space for different garment categories. So here is an example for shirts. So this canonical space is defined across different garment instances shared under a similar configuration. So here the configuration is defined by the garment geometry worn by a person in a T-pose. So as a result, this this shared canonical space allows the algorithm to learn a strong prior within each garment category that is independent from their own configuration. And so one way to understand this canonical space is that given a coordinate in this canonical space, it will map to a similar surface location for different garment instances, which means that for those locations, they're very likely to share a similar local geometry or semantic meaning. So for example, all the points on the shoulder will have a similar coordinate label in the canonical space. And in the later slides, you will frequently see some visualization similar to this, where the RGB color is basically corresponding to the XYZ location in the canonical space. So we use that to kind of visualize its canonical coordinate. So in total for this project, we consider 6 different garment categories provided by the Cloud 3D dataset. And then so with the post definition, now we can finally define the task, right? So given a partial observation of an unseen garment, the goal of the algorithm is try to map all the observed points to this category level canonical space. But then how about for the unobserved surface? Remember, we no longer have the rigid body constraints, therefore we cannot directly solve the position of those unobserved points using algorithms like RANSAC. So instead, what we're gonna do is that we will ask the algorithm to complete the garment's full 3D geometry in this canonical space. And therefore, as a result, it will provide the pose estimation for those unobserved surface as well. And then finally, we'll map this completed shape back to the observation space so that the output can directly describe the garment input configuration. So to summarize, the key idea for this project is to basically formulate this deformable object pose estimation task as a shape completion task in the canonical space. So by mapping the observed points into this canonical space, we can first estimate the pose for all the observed points. And then by completing the shape in this canonical space, we can estimate the pose for all the unobserved surfaces as well. So since the completion happens in the canonical space, the algorithm can leverage a much stronger shape prior that are invariant to the object configuration. So in the next few slides, I will cover a few most important design decisions for this algorithm. So first is how we can get input observation. So in this project, we are less interested about the task of unbodied class perception, where the class is already worn by a person. So instead, we are more interested in the garment under arbitrary configuration. However, if we do not pose any constraints on the configuration of the task, the configuration of the garment, the task can quickly become too difficult and in some cases impossible to solve. So instead, we will use very simple robot action to transform the class from their arbitrary configuration to a configuration that is more trackable for the perception algorithm. So what we do is to ask the robot to randomly pick up the garment from any location it can. And then by using this very simple pickup action, the system now is able to reveal more surface area on the garment by leveraging the gravity force. Basically, the gravity is pulling down the garment, and therefore you can see more of the surfaces. And then at the same time, this kind of pickup action itself is actually very simple and does not rely on any prior knowledge of the class or any knowledge about the class configuration. Therefore, it can be executed pretty robustly with almost 100% accuracy. And then after that, the algorithm will try to label all the visible surface with their canonical coordinates using a typical point net architecture. So also in this step, we can kind of propagate the grasp point from the observation space to the canonical space by using the predicted Knox label on that grasping positions in the input point cloud. And then the algorithm, after this step, the algorithm will need to complete the shape for this garment in the canonical space in order to provide the labels for the unobserved surface. So for this step, it's basically we are trying to do shape completion, and the task of shape completion for rigid objects is actually a very well-studied problem with many existing algorithms. However, for garments, because of their unique things 3D structure, it is actually a little bit tricky for selecting the right 3D shape representations to represent those kind of geometries. So for example, very obviously, occupancy grid is not a good choice for representing very thin surface, since its accuracy is directly limited by the voxel resolution. And on the other hand, using representation like sign distance function, we are able to represent thin surface structures by assigning different signs for voxels inside or outside the garment, whereas the zero crossing surface will basically precisely describing the location of the 3D surface. However, the problem for truncating sign distance function or like TSDF representation is that it can only represent a geometry that is watertight with no holes, or like watertight surface with no boundaries. And if we directly try to extract the zero crossing surface, we'll get additional surface around the garment's openings, for example, the neck or the waist. So to address this issue, we actually used a new shape representation called generalized bending number field, which will allow us to represent very thin structure, very thin 3D surface with openings. So what is bending number field? So the definition of bending number field at any given point is defined by the signed length of projection of a curve onto a unit circle. So the value will eventually normalize by 2 pi so that the final value is ranged from 0 to 1. So intuitively, to understand bending number field is for any point enclosed inside a closed surface, the bending number will always equal to 1. And for points that outside the curve, the projected bending number will always equal to 0. And then if we compute the bending number for all the locations in the space, we'll be able to get a bending number field. And we can also easily extend this definition to 3D by replacing the 2D angle with a solid angle in 3D. So the next question is why we use bending number fields and what are the special properties make it desirable for our application. So actually, if the surface is watertight, then the value actually, the bending number is actually constant 1 inside the surface and 0 outside, which is basically the same as occupancy grid, which is not as interesting or exciting. However, when the surface has opening, things get more like complicated or interesting. So for those surfaces, we can observe a smooth transition from the inside positive value to the outside negative value on the opening area. And in fact, this function is harmonic or smooth anywhere except the discontinuities on the surface. Therefore, by detecting the gradient on the bending number field, we can find both the surface and opening. And then by using the gradient magnitude, we can distinguish the surface, distinguish between the surface and openings. And here is a very simple examples of bending number fields that is computed on a t-shirt geometry and its corresponding gradient magnitude. You can see that the magnitude is significantly stronger around the surface compared to the openings like the neck and the waist. So by using that gradient magnitude, we are able to kind of identify which part is opening, which part is the surface. And here are some example results for shape completion step. And on the left is input coordinate prediction, canonical coordinate prediction, and the ground truth surface. And on the right, you can see the prediction results by using different shape representations. So what we can see is that with the bending number field, the algorithm is able to represent very thin surface and with correct openings. So in the last step, what we need to do is to map the completed 3D mesh from the canonical space back to the observation space. So eventually this output representation will describe the full configuration of this garment in the original observation space, including both observed and occluded part. So this is a final output. So in order to do this step, there is actually two possible approaches that is quite different from each other. So one one option is that we can use physics simulation, where we can use the predicted grasping point from the first step and the completed 3D mesh in the second step, and then simulate how the cloth will fall under gravity force, and use that to kind of describe the garment's pose. So the advantage for this approach is that it can always predict a result that is basically physically plausible. However, this method is also more sensitive to errors in the earlier steps, such as if the algorithm predicted any incorrect grasping points or invalid mesh reconstruction, those errors will be propagated through this physics simulation step. And the second approach, or a different alternative approach, is to directly predict the warp field as another implicit function. So basically, we're trying to predict the warp field for every single vertex on the predicted surface. So although this kind of predicted warp field may not always guarantee to be physically possible, but the network gains some additional robustness against the prediction errors happens in the earlier steps. So in our paper, we actually implement both method and comparisons quantitatively and qualitatively. So now I'm going to put everything together to form the end-to-end framework for GarmentNet, which basically consists of three major steps. So first is we will map the input point clouds to a canonical space using a point plus network. And then we will complete the 3D shape in this canonical space, and then finally warp the completed shape back to the input space. So the final output representation will describe the garment's full configuration using the completed 3D mesh with per vertex coordinate label. So here I'm going to quickly show you some of the results from GarmentNet. So this is the results for a dress. And for our training and testing, we are both most of the so all the training is done in simulation, and some of the testing is done in simulation as well. And also we do some testing in real world, which I will show in a bit. And here is another example of a skirt. A top. So here actually you can see that the shape completion does struggled with very thin structures on like the straps on this top. And here is actually a real world results where we actually captured RGBD images with a real world robot that's grasping a garment. And here is the shape completion results and their coordinate prediction. And here is more results from the real world data. And you can definitely find more additional results and visualizations on our project webpage, which is shown on the bottom on GarmentNet's webpage. So to summarize, basically the key idea for GarmentNets is really about the problem formulation, where we formulate the post-estimation problem as a shape completion task in canonical space. And then therefore, by leveraging the category level prior, the algorithm is able to infer the full configuration of an unseen garment, including both observed and unobserved surface. So this project, as you can probably tell, is mostly about perception. And the only step that involves the robot is actually the step 0, where we ask the robot to pick up the cloth in order to better observe it. However, this very simple action actually is very critical for the whole system to success, because it significantly reduces the difficulty of the perception task, right? Because it basically increases the visibility and also reduces the possible configurations of the garment. So this actually got us thinking, what if the robots, we give the robot more manipulation skills and allowing them to use their own action to physically unfold the garment, will this make the perception algorithm much easier? So that's actually lead us to the next project, which we will push more on the interaction side and trying to see how we can use a robot's physical action to actually unfold and reveal the unseen part of a cloth. So this project is called FlingBot, and my student Hui is going to present this work tomorrow in the Coral conference. So if you are going to Coral, please drop by to the poster session, and we can chat there as well. Okay, so the task we are trying to do for this project is cloth unfolding. Whereas the objective is very simple, just to maximize the visible surface area of a cloth. So as you can imagine, this task is actually very useful since it's almost a very typical common first step for almost any cloth manipulation pipeline, because by unfolding a cloth, we are able to reveal many key features on the cloth that are initially hidden or occluded, and therefore simplifying the later planning or perception steps. However, while the task or the objective is very simple, learning a policy that can effectively unfold arbitrary cloths is quite challenging. So here is just a very simple video of a 2-arm robot trained to unfold a t-shirt using actions like pick and place. So you can see that it actually takes the system a very long time, many steps to just make very small progress, right? So if the corners of the cloth is unfortunately not visible in the initial state, the system will not be able to make much progress with very long time. And similarly, if the cloth is actually larger than the robot's reach range, then the cloth will actually never be fully unfolded. So this system actually reflects a common limitation for many prior works in cloth unfolding, where the robot uses only quasi-static actions like pick and place. Right? So over the years, although there has been so many sophisticated algorithms and methods proposed to model deformable objects, the final system are oftentimes highly efficient, and they can easily take up to hundreds of steps just to unfold a very small piece of cloth. And so here is an example of the robot that actually takes, I think, 130 steps to unfold this very small piece of cloth. And as a result, many works in cloth manipulation actually considers a much simpler case where the cloth is almost already fully unfolded and the key features of the cloth are already visible in the initial state. But let's take a step back here and think about how would you unfold a very large piece of cloth like a blanket? So will you try to carefully pick and place every single corner of the cloth? Probably not, right? So instead, what you'll probably do is something very similar to this. So where you will grasp the blanket with 2 hands, stretch it, and then fling it over the bed with some high velocity actions in order to fully unfold it. So from this example, we can see our system is really missing is the capability of using high velocity dynamic manipulation, which is something that we as humans are constantly using in our everyday lives in order to improve our physical reachability and action efficiency. So fundamentally, what dynamic manipulation gives us is the ability to use high velocity action to control under-actuated objects without direct contact, and therefore efficiently expand a system's reach range. So using this idea, we designed our system called FlingBot, which is a fully self-supervised system that is able to achieve over 80% coverage, unfolding coverage within 3 interaction steps. So in our experiments, we used 2 UR5 arms and 2 RGBD cameras for the physical setup. So for these 2 RGBD camera, one of them will take a front view image of after the class has been picked up, and the second one will take actually top-down images used for predicting grasp positions and compute reward. So what the algorithm need to do is to take the top-down image as input, and then output the parameters for the Fling primitives, which we'll talk in a bit. And then after each of the interaction, or after each action, the top-down camera will try to capture the image of the class before and after the interaction, and then compute the delta coverage of the class, and then use that as a supervision signal to supervise network training. So basically what a bigger delta coverage will translate to a higher reward. And then in the end of each episode or training episode, the system will automatically reset the class initial state by randomly pick up the class and drop it back to the workspace. So the whole system is able to learn only with self-supervision or with minimal human intervention. So our dynamic dynamic Fling primitive actually consists of several steps. So which is stretch. First pick up the class, stretch the class, Fling, and then place it back to the workspace. And then, basically, in order to learn how to do these Fling actions, the system needs to learn where to pick, how to stretch, how fast to Fling, and where to place. However, for the task of class unfolding, there's actually already some trivial answers for some of those primitives. So for example, for the step 2, we just want to, because we want to do unfolding, therefore we just want to stretch as much as possible. And then similarly for step 4, the algorithm can just place the class somewhere in the workspace so that it can be picked up again. So what the system really need to learn is basically where to grasp and also how to Fling. However, in our real-world experiments, we observed that the grasping position or predicting where to grasp is actually more important to learning the actual Fling speed or Fling parameters. Here is a quick experiment that we did in real world, where we basically change the Fling height and Fling speed manually, and the system can still perform reasonably or achieving very high coverage from a crumpled initial state as long as the grasping point is good. So based on this kind of observation, we actually fixed the Fling speed in most of our experiments, and instead we'll just focus on learning to choose where to grasp. So basically what we are doing here is we decompose this very complex multi-step Fling primitives to a much easier task, basically learning where to grasp. Okay, so now we have the problem of learning where to grasp, but however, in order to really choose a good strategy for bimanual grasping that's able to achieve a good Fling or unfolding result, it is still actually a non-trivial task. In particularly, we need to consider how to design the action primitives or like the action representations so that they can avoid the collisions between these two arms. So there are a few constraints that we would like the grasping strategy to follow. So first is crossover constraint, means that these two arms shouldn't cross over each other. The left arm should always maintain the left. And the second constraint is grasp width constraint, which is also very simple. Basically means that the two grasping points shouldn't be too far or too close to each other. So given these two constraints, what we need to do now is to design our action parameterization that can easily satisfy those constraints. So a straightforward formulation will be directly predicting the left and right grasping point independently. However, the constraints under this formulation will get entangled together, and it will be actually quite hard to filter out the invalid predictions afterwards. So instead, what we do is to use another formulation, which basically predicting the center point of the left and right grasping point, which is labeled as C, and then additionally predict the angle of between these two grasping points and the grasp width. So the angle will represent as a theta, and the grasping width will represent as W. So this parameterization will allow us to compute the left and right grasping point using very simple trigonometry, and they are always satisfying all the constraints that we listed above. So now the task is trying to learn the parameters of C, theta, and W. So one approach, again, is to directly predicting all these parameters as a regression task. But of course, we can do better than that, right? So where we can, so the goal is that to use the structure of the problem in order to inject some inductive bias to this learning process to improve the learning efficiency. So in particular, we observe that the task for class unfolding actually satisfies a few equivariants with respect to the inputs. So for example, we want the grasp to be translational invariant, which means that if the class is shifting around in the workspace, the grasping point should be shifted together as well. And similarly, we also want the grasping point to be equivariant to rotation and scale. So in order to implement this idea and maintain this kind of equivariance, we use the spatial action map as a value network to evaluate all the grasping candidates. So the idea of spatial action map is that whenever you try to reason about the rotations or scales in the output, you can offload this kind of reasoning to transform the input instead. So instead of rotating or scale the grasping parameters as the output, we can rotate and scale the input image and then infer the scores for a fixed grasp parameters. So here is how we apply it to our problem. So given an input image is a top-down image of the workspace, we can scale and rotate it to obtain a collection of transformed input image. And then we can feed this all the collection of images to this value network to predict the grasp score. And then so here the scale will corresponding to different grasp width W, and the rotation will corresponding to different grasp angles theta. And then the output of the network is a dense value map, where each of the pixel corresponding to one possible center locations for the two arm grasps, which is corresponding to the parameter C. So the action selection is done by simply pick the action with the highest grasp value among all the scales and rotations. So this value network is trained to directly predict the delta surface area with the self-supervised signals that we talked about earlier from the top-down camera. So we trained our system first in simulation. So here is the simulation environment that we used for training and also application study. So our policy is trained on rectangular cloth of different sizes. And we also explicitly test the algorithm with a very large rectangular cloth that is actually larger than the system's maximum reach range. And lastly, we also test the policy on shirt, so which the system is never trained on. So the algorithm is only trained on rectangular cloth, and we just directly test on different shape of shirts. So in this talk, I will skip the evaluation on simulation, but directly jump into real world experiments, which is more interesting to look at. So here we compared our system, FlingBot, with a system that only uses quasi-static actions like pick and place. And in the plots in the bottom, we actually shows the class coverage with respect to interaction steps, which basically indicates efficiency of different policies. So you can see that right now the FlingBot already finished unfolding this class, but the pick and place system is still trying to make progress. And they actually get saturated around 60%. And here is another experiment with a much larger cloth. Yeah, again, FlingBot is able to fully unfold it within around, let's see, I think it's about 4 steps, but the pick and place is still struggle making progress. And the last experiment is on shirt. Just remember that we never really trained the algorithm on different like garments or shirts. It only trained on rectangle cloth. And the system actually directly work out of the box that able to handle different type of geometries. And here are just more results and the videos. Actually, if you want to see more videos of FlingBots in action, you can actually check out the webpage. There's a lot more videos online. And they're actually pretty satisfying to watch. So here are some quantitative results and comparisons. So in our paper, we actually compared our algorithms with 2 quasi-static baselines, which is pick and drag and pick and place. Here we also include a variant of our approach, which actually explicitly learns the optimal fling speed on top of the grasping strategy using reinforcement learning. However, what we can observe is that it doesn't really do some significant better than the FlingBots that do not predict optimal fling speed. As a result, we just directly use a simpler version as our final approach. So to summarize, the goal of FlingBots is to basically demonstrate the effectiveness of using dynamic manipulation for class unfolding through a self-supervised learning framework. So more specifically, we show that they are able to improve the system's efficiency, increase its effective reach range, and also achieve a good generalization capability for out-of-distribution class that the system has not trained on. So far, we have talked about one project on class post-estimation, which is mostly perception, and also a project on class manipulation. And so far, they have been studied, I would say, pretty separately. However, I'm pretty excited about the potentials of combining this perception and the manipulation system in order to achieve a more robust and versatile system. So in the next few slides, what I'm going to do is that I will first describe some of the major limitations for each of the system. And then I will discuss how those kind of limitations can be addressed actually by effectively integrating these 2 systems together. So first, for GarmentNet, the perception project, one of the biggest limitations as is now is its strong reliance on simulated data for training. So because the algorithm actually needs dense correspondence label as supervision, it is actually quite hard to collect such labels for real-world training. So as a result, I think it is probably one of the biggest bottlenecks to prevent the algorithm from achieving better real-world performance. And then for FlingBot, since it's designed for only trying to maximize the class coverage, the algorithm actually do not explicitly aware of the actual configuration of the class, which means that it cannot really handle tasks that has higher precision requirements, such as goal condition folding. Right, so what it can do is to unfold, but it doesn't really understand the pose or the configuration of the class. So in an ongoing project, we really aim to kind of address all this, both of the drawbacks through our interactive class perception framework. So here is a very high level idea. So on the one hand, well, what we hope to do is to use this kind of dynamic actions in FlingBot to help us to collect the real world training data for perception algorithms such as a GarmentNet. Right? So with a system like FlingBot, we have shown that the system can always kind of reliably reset the class state in a canonical unfolded state within a few interactions. And then under this kind of state, the algorithm can easily map its visual representation into this canonical or coordinate space representation. And then after that, when the robot is trying to pick up the class again, we can automatically compute the Knox label for that pick point location, and therefore provide the labels for training the algorithms like GarmentNet. And on the other hand, we can also combined perception algorithms that is able to estimate the pose of the garments with dynamic actions in order to enable more precise manipulation or more efficient manipulation. So for example, here is if we are able to estimate the cloth pose, then the estimated pose can also be used to inform garment-specific grasp strategies for different manipulation skills. And for example, grasping on the shoulders is particularly effective for unfolding t-shirt. So here is just one example, but there are many other manipulation skills that maybe will prefer different kind of key points. And then in addition, with this kind of pose estimation, the algorithm will also be able to kind of directly manipulate those semantically meaningful key points in order to fold the cloth into specific goal configurations. So while the plan or the idea sounds pretty exciting, I have to say that there's also a few significant challenges or interesting technical challenges that we really need to address in order to achieve this goal. So first is how to scale up the data collection process so that it's actually sufficient for training deep neural networks. So instead of getting only one labels for each interaction step, can we actually kind of amplify the ground truth labeling process through methods like cycle consistencies or domain randomization? And then for the second part, where we try to use the estimated pose for manipulation, the challenge there is how to give the perception algorithm the ability to reliably estimate its prediction uncertainty, which is oftentimes very critical for downstream planning algorithms. So for example, this kind of uncertainty estimation can help the algorithm to make simple decisions like whether it should continue to unfold the cloth to obtain a better observation, or it actually in a state that it should start to fold based on the estimated pose, right? So that can be that kind of decision can be made based on this uncertainty or confidence estimation. But most of the perception algorithms actually do not provide those kind of uncertainty estimation. So as you can see, there are still many open challenges in this direction. And I think so far I probably described more problems than solutions. And in particular, I think given that you guys are all a lot of you guys are actively working on this area of deformable object manipulation. So what I want to do now is kind of open the floor for discussion. And I would really like to hear your ideas and suggestions about how we should really approach this problem. So that's the end of my presentation, and I would like to start the discussion.